Welcome back, Hampshire chemistry students. Today we're going to be continuing our look at gas laws. Specifically, we've already talked about our Boyle's law, which relates pressure and volume. Remember, this guy has a constant temperature. We have Charles' law, which relates volume and temperature, where the P is constant, and Gay-Lussac's law, where pressure and temperature are related and we have a constant V. But something you might have noticed is that in a couple of the problems in our labs, that sometimes it's hard to figure out, hey, I'm not sure if pressure is constant or volume is constant. It seems like sometimes they're all changing. So sometimes I need a law that can actually relate all three of these. And that's where our new best friend, the combined gas law, comes into play. It is a combination of all the other gas laws because it relates pressure, volume, and temperature. And we can tell when we need to use it because there are no constants, when everything is changing. So what we're going to do to write this equation is actually very simple. You might have noticed that a lot of these kind of follow the same pattern. Temperature is always on the bottom, P and V are always on the top. So our equation for the combined gas law is very simply a situation where you have what looks like Boyle's law on the top, but then you include a temperature on the bottom, so our T1 down here. And this is going to be equal to our P2, V2 over T2. Okay. It looks like a lot, okay, but we're going to be using the exact same types of math that we were in our other examples and using those to help us get the correct answers. So let's take a look then at our combined gas law homework. Okay. Why don't we go ahead and write that equation up here to remind us. Okay. So our goal here is going to be solving our problems using the combined gas law. Okay, let's take a look at a problem like number 1. Okay, it says the pressure of gas changes from 120, so that's going to be my P1, and then it's going to 50 kPa. Okay, I hope that you are writing your variables with me, so I have my P1 and that I fixed to my P2. We then have some volume changes, right? So if we were on a normal problem, we might think, oh, I'm using Boyle's law. However, it continues and says, hey, here's our initial temperature. What's the final temperature? So I know right away that since that all three of my variables are changing, I'm going to be using the combined gas law. Okay, now I hope you're into the habit now that once you see a degree Celsius in the gas law, you're like, whoops, let's make sure we're going to add 273 to our temperature here. So, we have 81 plus 273. That's going to be 354 for our T1. So that's 354 Kelvin for T1. Okay? And we're looking for that new temperature, that T2. Okay? We've got our problem outlined. All we need to do now is rearrange our equation. Okay? It looks scary, but let's go ahead and write it out. Okay, but we're actually going to use the exact same method that we used in our other problems. Okay, all we're going to do is I've got two fractions on either side. Let's get rid of these fractions by cross multiplying. So I'm looking for this T2 here. So I'm going to take P1 V1 times T2, right? These are across from each other, and that is going to be the left side of my equation. I'm going to do the T2 in blue just so it pops out a little bit more. And that's going to be equal to the other cross. So T1, P2 times V2. Okay. Pretty straightforward, because now all I got to do is I got to divide anything over that's not T2. You could do them one at a time, but let's just save that time. And let's divide both of our P1s and our V1s over. We're just canceling out what's over on this side and moving it to over here. So I've got my equation all rearranged. It's got lots of variables, which is why it's so useful to do this before we plug any numbers. Trust me, if you try to plug in all your numbers with all your units, it gets very confusing very quickly. So now that we've got our equation set up, let's go ahead and solve for T2 here. And all I'm going to do is just go back and make sure I labeled everything. I'm taking my T1, my 354 Kelvin, times the P2. Careful that you're using, not pulling the P1 by accident here. Our equation setup says we're going to take the P2. So we're taking the 50 kPa, and then we're multiplying by the V2, that's the 40 liters. And then we're dividing by the P1, which is the 120 kPa, and we're multiplying by the V1, that's the 45 liters. Okay? Now that we have our numbers all set up, we can check to make sure our units work out. Okay? So kPa cancels with kPa, liters cancels with liters, and I'm left with the temperature unit, which makes sense because I'm looking for that T2. So let's figure out what this is. Now it's the calculator's job to come into play here. So we have our top part of our equation. I'm just going to go ahead and type all of that out into my calculator. Okay. All of these guys coming together are just going to go ahead and hit enter on the top, and then we're going to divide by the bottom. Now you could put this in parentheses, but my favorite way is just to keep going. It's taking the answer from the last one. I'm going to take 120, and I'm going to hit divided by again in order to divide by 45 as well. And we get an answer of 131. Let's go ahead and bring that down. Okay. Now, we're pretty much on the home stretch here. You're like celebrating with all your friends. Hey, I got the answer. Let's go ahead and check. Uh-oh. We're way off here. Let's reevaluate. Okay. We checked our units up here, right? That makes sense. Okay. This was a K, but wait. Our problem didn't ask for K. Make sure we're looking carefully at these types of problems. Sometimes we need to sneak in here and say, oh, it didn't ask for the temperature in Kelvin. It asked for it in Celsius. So in order to go from Celsius to Kelvin, we add 273. So to get rid of Kelvin, we're going to go ahead and subtract 273. And minus 273 gives me that negative 141.8, which I'm going to round up to negative 142 degrees Celsius. Okay? So hopefully that we can see here that this problem is no crazier than any of our other gas law problems like Charles or Gay-Lussac's where we needed to cross multiply. Okay? We have a couple more variables in play, which is where we get, if you're keeping your units organized and everything's coming out, you will do absolutely fine. Right? Make sure, like at the end of this one, you're reading carefully. What did the answer want you to find it in? Okay, so, for example, you might need to do some conversions between milliliters and liters in certain problems to make sure that you're matching what the answer is looking for. Keep that in mind. Keep your units careful, and you're going to do awesome. Okay? This is all you now. You can handle it. Take some time on it. Have a great rest of your day, guys.